In this video, I want to show you how to approximate the largest Lyapunov exponent of a dynamical system using Jax's Autodiff engine. We're going to discuss it and implement it, and then compare how it converges against an estimate from the literature. Let's get started. The channel sponsor Pasteur Labs is currently hiring SciML and software engineering positions. Check out pasteurlabs.ai/careers for more details. Hi and welcome to this new video in which we will again approximate the largest Lyapunov exponent of the original Lorenz system, but this time using the Runge-Kutta simulator we wrote in Jax and also making usage of Jax's automatic differentiation engine. Recall this Lyapunov exponent was a quantity to measure how quickly and ever so slightly perturbation in the initial condition grows or diverges over time. And this time we're going to approximate it with the following idea that it will be given approximately as the mean, so taking a summation and then dividing by the number of entries of the logarithmic growth in a perturbation trajectory. And this will be different from the last video in which we had actually two trajectories evolving independently from each other, starting at slightly perturbed initial condition. But this time we will have a main trajectory that evolves, and we will use the dynamics or the state of the main trajectory to define a tangent linear dynamics, which evolves alongside, and we're going to propagate the tangent all the time at each time step and then measure how it grows. And with this approach, we can also approximate the Lyapunov exponent. So as said, we're going to have this perturbation trajectory here called epsilon, and this evolves according to the Jacobian dynamics. Let's just discuss the strategy, and I guess most of it will become clear once we will implement it. So we will start, like in the last video, by drawing a reasonable initial condition, which is, for instance, 1, 1, 1. And then we're going to evolve it for a couple of time steps to get on the chaotic attractor and then reset the initial condition and consider this as a warmed up state. Then we're going to introduce this small perturbation epsilon by drawing random noise, but we will then normalize it to have unit length such that it, in our case for the Lorenz system, will be a three-dimensional vector or three-dimensional random vector, but with length 1. And now comes the tricky part. So we will now use this warmed up u0 to integrate over time, but each time we go to the next time step, we will not only advance the u state, but we will also advance the epsilon state next to it. And that works as follows. So obviously we will get the next state in time by applying the Runge-Kutta simulator on the previous state in time. So ut plus 1 is this calligraphic p applied to ut. But at the same time, we will also compute the Jacobian of the time stepper. So basically, we will employ the automatic differentiation engine of Jax to get the Jacobian of this advancing routine evaluated at the previous point in time. And this is also the reason we need to integrate this perturbation trajectory alongside the original trajectory, because each time we want to also advance the perturbation trajectory, we need the information from the original trajectory. And then, as said, we can advance the perturbation trajectory by using the Jacobian of the time stepper and multiplying it with the perturbation at the previous point in time. We're then going to renormalize the growth, or we're going to renormalize the perturbation. And this is primarily done in order to not have the perturbation grow very large, because obviously the perturbation will grow. And by renormalizing it, we can measure how much it has grown in this one step. And then basically by this very formula, we will just average over a lot of steps. And we could potentially also have this approach run indefinitely to really get a long trajectory and a long estimate. We will do this integration for a couple of steps. So let's say, for instance, 50,000 or 500,000, and we will record the growth in the perturbation norm. But since we renormalize each time step, this is precisely given by the norm after the application of the Jacobian dynamics. And then we can just apply this formula to compute the approximate Lyapunov exponent. And then after we've implemented this, I'm also going to show you a nice trick in how we can do step 5 more efficient by using a core idea of automatic differentiation. Okay, let's get started with the coding and go down. So I kept some parts from the previous video where we implemented the Runge-Kutta 4 simulator in JAX. So let's just re-execute them. So first the imports, then we defined the right-hand side and then implemented the numerical simulation in terms of an autoregressive time stepper. So that was a very simple class with a call signature that produced the next state and time based on the previous state and time. Then we can instantiate them, and we also did a very simple trajectory in the previous video. We also started at this once state, and then just to recall what happens, we can use the instantiated stepper to apply it to the 3-dimensional vector and produce another 3-dimensional vector. And then in the previous video, we also discussed a simple function or function transformation, to be precise, that performs the autoregressive rollout for us, that uses this very efficient jax scan routine, and that was then used to produce the trajectory. And in the spirit of the rollout transformation, I want to implement a similar transformation, which not only produces the trajectory, but next to it like evolves this tangent linear dynamics. So let's go down and call this rollout with growth. And this one also takes a stepper and a number of time steps. This time we will not implement this functionality to include the initial condition. And then what should it do? So again, we need to define a scan function, which will then be called in the scan routine. So let's start with that. Define the scan function. And the scan function in JAX always takes 2 arguments. The first one is a carry, which comes from the previous iteration, and then it gets some external input, which is given when we call the jax.scan function. So for instance, if you used the jax.scan to do an autoregressive rollout of a time stepper, this could be used to supply some time-dependent forcing information. But in our case, we don't have that, so I will just leave a placeholder here. And then within the carry, if you look at it, so in the jax.scan function for the rollout, the carry was the state, but this time we basically have 2 variables that's going to be carried. So we both have the state as well as this epsilon, so this perturbation. So let's unpack the tuple and say u and epsilon is carry. And then we have to both advance the u state as well as the epsilon state. So u next, quite obvious, is to apply the stepper to u. And in order to advance epsilon, we first have to compute the Jacobian. And we will get the Jacobian by saying jax.jack forward, so using the forward accumulation for the Jacobian of stepper applied to u. So this one here is also a function transformation. And we then evaluate the Jacobian at the current point in time. And then we get epsilon next by multiplying the Jacobian, or precisely matrix multiplying the Jacobian with epsilon. And then essentially, since we always assume that the previous epsilon is normalized, so it has length 1, if we now measure the length of epsilon next, we get the growth in epsilon. So let's call this the growth. And this is jnp linalg.norm applied to epsilon next. And handily, we can also use the growth to normalize epsilon next. So let's do epsilon next and maybe make it precise that this one is normalized, which is epsilon next divided by growth. And then essentially, the scan function has to return a carry as well as something to stack. Of course, we want to pack the carry similarly as we also got the carry. So let's say carry next is going to be u, not u, but u next, epsilon next normalized. And then we can return the next carry. And we also need to return what we're going to stack. And since I want this function to provide both the rollout of the state, so the trajectory, and also the growth in our epsilon variable, we're gonna return both and say uNext together with the growth. This concludes our scan function, and then we can implement the function which will then be returned as part of this function transformation. So let's call this the rollout with growth function. And this one now not only needs an initialized point, so a u0, it also needs an epsilon 0. And then it first has to produce the initial carry. So this is the one we're going to supply to jax.scan. And this obviously consists of the initial state as well as the epsilon 0. And in order to ensure that it is normalized, we will normalize it here by dividing it by its norm epsilon 0. Then we can call jax.scan using the scan function. And as the init, we will of course use the initial carry. And then we will set xs to none. So this is basically the array you would provide the external forcing. So that would be then supplied in each time the scan function is called. And we will set the length to n, as we define it up here. And this returns then two things. So first it returns the final carry, which we are not interested, but rather we are interested in the u trajectory as well as the growth trajectory. Let's just call it trajectory and growth trajectory. And then this transformed function should return both the trajectory and the growth trajectory. And ultimately our function transformation should then return the transformed function, which is this rollout with growth function. Okay, cool. With this function, we can then produce this epsilon trajectory. But first, according to our steps, we want to enter the chaotic attractor. So let's use our 111 initial condition and evolve it for 5000 steps to get a u0 warmed. And for this, we will just say rollout. So the original rollout without pushing the epsilon, and apply it to the Lorenz stepper for 5000 steps, and then apply it to the u0, and then we will just simply index it at -1 to get the last index. You can also take a look if you want. So it's again a 3-dimensional vector, but it should now lay on the chaotic attractor. Cool. Then let's use this u0 warmed in our rollout with growth function to produce both the warmed trajectory as well as the growth trajectory by saying rollout with growth applied to the Lorenz stepper. And for instance, let's be crazy and do 500,000 steps. So it's a very small system, and Jax is efficient enough even on this laptop CPU to handle this in a fraction of a second. And then we need two inputs. So we will need the u0 warmed input and also an initial epsilon. And here, as I also mentioned in the intro, it is fine if we take a random normal noise. So let's do jax.random.normal, for which we have to supply first a random key. So jax.random.prng key. Let's, for instance, use 12, so this does not really matter here. And then we need to provide a shape, and this will be a 3-dimensional vector because it has to have the same shape and size as the original state vector. Then let's execute that. And as you see, it runs in a second, so it's very fast for these 500,000 time steps. Let's take a look at the shape. So warm trajectory.shape and growth, let me scroll down, growth trajectory.shape. So this one is 500,000 by 3 because it has, for each time snapshot, it has the corresponding state. And then the growth trajectory has 500,000 entries because for each point in time, it has the scalar value, how much this epsilon value grew. With these 500,000 values, we can then apply the formula here. let's do exactly that. So to be precise, in this formula, it showed what was the growth in the magnitude of the epsilon from one step to the next one. But since we always normalize or assume that the previous state was normalized, it is just sufficient if we take the logarithm of the growth we recorded. So let's do exactly that. We can get a Lyapunov approximation by taking jnp.mean on jnp.logarithm, and logarithm by default is the natural logarithm of the growth trajectory. And then let's take a look at the Lyapunov approximation. And then you see it is 0.00908. And if you recall from the previous video, the Lyapunov exponent for the original Lorenz system should be roughly around 0.9. And we see here it is off by 2 digits or by 2 orders of magnitude. And that's of course because we have to rescale it with the delta t that is in our stepper. So let's do this and say Lorenz stepper dot dt. Sorry, not multiply, but we have to divide. And here we go. Then we get an approximation, which is 9082. This is, of course, like the way how you would use the entire trajectory. But now it's also interesting to look at how the value develops over time. And for this, I want to compute the cumulative mean over the growth trajectory, such that we can look at what is the approximation of the Lyapunov exponent based on how many time steps we do in this approach here. For this, I will first compute the logarithmic growth trajectory, which is just applying the natural logarithm to each entry. And then I will compute the cumulative mean log growth trajectory. Unfortunately, there's no cumulative mean function in jax.numpy, but we can get around with that. And by just saying jnp.cumulative sum over the log growth trajectory. And then we have to divide it by the number of elements at each point, which is just given by an arrange command. So jnp.arrange, and then we need to do as many as we have time points in this log growth trajectory. So length of log growth trajectory. And then we will get the Lyapunov approximation trajectory by taking this trajectory and multiplying it with, or sorry, again, dividing it by the time step. So Lorenz stepper.dt. That takes a second, and if we take a look at it, so we see that it basically starts, and it starts at -infinity. That's of course because I had arrange start from 0, so we have to do arrange from 1 to the length +1. And then we get rid of the infinite here. And basically you see in the beginning the approximation is rather bad, but over time we see it seemingly converges to something. So at least for the last 3 entries here, the 3 digits after the comma seem to be fixed more or less. Let's display in a plot what it thinks the Lyapunov approximation is after specific number of time steps. So let's do plt.plot on the Lyapunov approximation trajectory, activate the grid, and activate an x label and say, sorry, an x label and say this is time step, and a y label which is approximate Lyapunov exponent. Let's run that, see what we get. So we see that in the beginning, also what we got from the values in the trajectory, it seems to be far off from the true value. And then after, I'd say roughly 1,000, 2,000 steps, it seems to be less strongly oscillating in this magnitude. To maybe make this a bit nicer, I will just index it from 2,000 upwards to get rid of this initial highly oscillatory regime. And then we also see that, well, now there's still oscillations left, but at least they are way smaller in magnitude. And over time, it seems to find its value. That's because of these this cumulative mean that we employ here, that we have all the history information of the approximation so far. And it seems to be more or less converging, at least this is what the linear plot might indicate. And so we see that maybe approximately we get the value already after 100,000 steps. And you see it is in the range where we expected, so slightly above 0.9. As you recall from the previous video, typically the true Lyapunov exponent for the original Lorenz system is 0.9056. Let's compute the difference of the value we obtained from this true value. So let's call this the difference and say this is jnp.absolute of the Lyapunov approximation trajectory minus the true Lyapunov exponent. And then we can plot that in a semi-log y-plot. So that is nicer because now we have a logarithmic y-axis, so we can really see how the error goes down in orders of magnitude. So let's do the diff, and again I will exclude, or maybe we can also leave them for the start and activate the grid. Then the x label is again time step, and I will scroll down. The y label is then the absolute error from the true Lyapunov exponent. Let's shift enter that. And here we go. So in the beginning, the value of the error is quite high, so it's approximately 10 to the 1, but to be fair, we also start with this random normal noise, and we of course need to somehow get a certain momentum building up of our estimate. But we will see that after roughly 50,000 steps, our error is already under, or on average, under the 10 to the minus 2. It of course has some very strong peaks down here, but it's of course because it is so oscillatory. And then over time, we see it keeps oscillating, but that's of course natural because we have the Lorenz system, which has this chaotic attractor, which some sense has some periodic effect to it. But eventually we will see it will not get much better than a little over 10 to the minus 3. And that is also reasonable because we saw that the approximation is 0.908 and the true value is 0.9056. So it is correct up to 2 digits after the comma, but starting from the 3rd digit after the comma, it gets incorrect. And this is then reflected here that roughly something in between 10 to the minus 3 and 10 to the minus 2 is where our error will converge to. A typical question you might ask, like how one could get a more precise estimate. There is a cheap way to do it. So what we can do is we can switch to Jax's double precision mode. So let's go all the way up here and say jax.config.update on Jax enable x64, which enables double precision for Jax, and we will set it to true. And if we then rerun the entire notebook, and I hope I'm quick enough, and we go down here, and then it gotten slightly better. Let's take a look at what it estimates now. So now the estimate is at 0.906. So before we had 0.908. So it is now closer to the 0.9056. So if you were to round that, you would get 0.906. So one could now say we are precise up to 3 digits after the comma. Then of course, interesting question, how can we get even more precise? And typically what you would do is you would rerun the entire experiment of approximating the Lyapunov exponent with a different initial condition or with a different perturbation, and then average over all the samples you get. And then you should be getting a more precise estimate. Or of course you could try to use a smaller time step or use a higher order integration method. But I guess for this very simple approach here, getting 3 digits after the comma or 2 digits with single precision floats is already quite sufficient. As I mentioned in the intro, there's one last performance hack I want to do. And for this we want want to go up to the rollout with growth function. Here we have to propagate both the state u as well as the perturbation epsilon. And for this, we first call the stepper to get to the next state. Then we build the entire 3x3 dimensional Jacobian matrix, and then we make a matrix vector product here. And this is very inefficient because in order to build the entire Jacobian matrix, Jax will again call the stepper on U, and on top it will also do 3 so-called Jacobian vector products. I will have a video linked up here if you're interested in that. So ultimately, if you say that doing one Jacobian vector product evaluation is approximately the same cost as calling the stepper in the first place, we do one stepper call plus another stepper call plus 3 Jacobian vector products, let's say 5 stepper calls, and then we do a matrix vector product, which, if it gets larger, is also of significant computational burden. And the reason I'm saying this here is because for this particular thing we're doing in propagating, also calling both the stepper with a primal input and also propagating a tangent information, this is essentially the primitive of forward mode automatic differentiation. And if we use this primitive, we save a lot of compute. So how does that work? So first I will comment out these 3 lines, and then essentially we want to employ the function Jacobian vector product. If you want more details, I also have a video linked up here. What does that function do? So it does exactly what we do in these 3 lines here. It takes a function, in this case, this is the stepper function. It evaluates it at a primal input, which in our case is u, and then also takes a tangent input, which in our case is epsilon, and returns u next as well as epsilon next. And it does so way more efficiently than we have here. Okay, let's see if it produces the same result. For this, I want to comment out the 64 double precision mode, and I will just restart the kernel because otherwise the configuration of 64 double precision is still enabled. And if I then rerun the entire simulation, and if I go all the way down here, let's take a look at our approximation is here. So it takes a little while until we go there. And we see there is an error. Oh yeah, of course. Sorry, I forgot to add a comma. So of course we need a comma here. So maybe also let me explain this in a second. So we need these tuples because we could potentially have a function that we want to transform which has multiple inputs. So for instance, if the stepper also took, I don't know, a forcing information, for instance, then we would also have to supply a tangent on the forcing information. But with that one, it should work. Yes, and it does. Let's just shift enter all the lines here. And let's see what is our approximation. So the final approximation is .908 again. So conceptually, it still does the same as what we had in the code before. But of course, now we save some compute. I mean, arguably, in this very simple example of the Lorenz system, this is not noticeable, but imagine you were to apply this approach here to a way larger system. So for instance, for a chaotic PDE system, like in turbulent simulation, turbulent flow simulation, or the Kuramoto-Sivashinsky equation, then this of course is extremely important that you make sure that you can get your push forward or detangent propagation as cheap as possible, because the cheaper you can get it, the longer you can have the trajectories running, so the more precise your Lyapunov approximation can get, or the more examples you can run to also average and get an even preciser estimate.
This channel is supported by Pasteur Labs and the Institute for Simulation Intelligence. Click the link in the video description to find out more how they merge machine learning and simulation in order to reimagine the scientific method. Also, a big thanks to all my Patreons. If you also want to support my vision of free education on advanced mathematical topics, you find the link to the Patreon page down in the video description.
I hope you enjoyed this video. If you did, then please leave a like and consider subscribing to the channel. There is more awesome content on dynamical systems, all kinds of machine learning, and automatic differentiation. Here you will now find similar videos, and I hope to see you in one of the next videos.